You know, right down the field, the road is the Battle of Princeton battlefield. Washington crossed the Delaware maybe 15 miles from here during the Revolutionary War. All right. So those of you who were here yesterday, that's my quick summary of what we talked about up there. So fuels are a big problem and also a big benefit. And we have a pretty good system right now for making fuels, supplying fuels. Lots of people drive cars and take airplanes, and trucks drive around. It all works fine. Except we have kind of local pollution problems. There's some question about how long the fuel will continue to be affordable. And also, we're gradually pumping all the carbon that's under the ground up into the atmosphere with unknown but probably not positive implications for the climate. And so this is not really sustainable long term. So we need to do something. And one thing we can do, and I'm sure many of you are working on this already, is try to improve the efficiency of the current system so we don't have to pump as much CO2 into the atmosphere to get the same benefit to society. And so that's all about trying to make more efficient engines, trying to make the fuels more efficiently. So that, anyway, that's huge benefit, basically no downside to make the whole system more efficient. The other little bit more extreme thing to do is to try to find a new energy carrier for transportation. So how are you going to carry your transportation energy with you? I guess one way is not to carry it. So you could have trolley lines with overhead wires everywhere. And in fact, that's how the transportation system in this country worked around 1900. But people decided they liked the freedom to be able to drive any direction they wanted to and not have to keep going straight on the trolley tracks. And so basically, we ripped out most of the trolley tracks in this country and replaced it with roads so people could travel around. So then you have to carry your energy with you if you don't have a wire, if you're not plugged in. And so there's kind of two ideas here. One idea is to use batteries. And that's definitely a viable option. But batteries are expensive. Batteries are heavy. The power output from batteries, it's difficult to make the power output really high. The battery guys are working on it. So it's a possibility, but I would say you might hope that there's a better option. Another option would be to find an alternative fuel, one that was not based on pumping fossil fuels out of the ground into the atmosphere. Now, this is actually pretty challenging. One idea is biofuels, where the plants are pulling the CO2 out of the atmosphere already, and so you don't have to use any fossil carbon net from the biofuels. So that's a possibility. Calculation shows something like maybe 20% of the transportation demand could be met by using biofuels. Maybe there'll be some breakthroughs in trying to improve that. For example, some people work in algae. Anybody here working in algae? So anyway, algae has a potential to exceed that considerably, but has millions of technical problems. So I don't know if it's actually going to do it, but at least potentially you can make a lot more carbon. You could suck a lot more CO2 out of the air by growing algae. Another idea would be to actually make a completely synthetic fuel that didn't have carbon in it at all. So one idea is to use hydrogen, and former President Bush was a big advocate of this. This has a lot of problems because hydrogen is actually not a very high density energy carrier. So you have to compress it to high pressures or liquefy it or something. And so that's a problem. But when you burn hydrogen, you definitely don't make any CO2. So that's pretty good. Another idea is to try to make things out of nitrogen and hydrogen, so like ammonia or hydrazine. And those look actually pretty good. You have very high energy densities. They burn well. People have experience with it. It's a rocket fuel. It's poisonous. Ammonia was used as a poison gas in World War I. Has some downside. But maybe it's worthwhile. And in fact, I know there's some projects going on right now to try to work on those. A big issue there is to make sure that you really control the NOx emissions and burn all the nitrogen to N2 and not to NO. Otherwise, you'll exacerbate the smog problem. But maybe that's another possibility. Anyway, whatever you decide to do as your alternative fuel, you have to know how it's going to behave. And if you want to assess proposed alternative fuels, you have to be able to know it. And so the motivation for what I'm going to tell you about today and tomorrow is all about trying to be able to take some new proposed fuel and try to predict what it's going to do in some new engine. And this is relevant both for improving the efficiency. So if you want to assess new engine designs, you want to know how the fuel is going to burn in the engine. And also relevant to alternative fuels, because if you're going to change the fuel, you obviously need to have a model that's sensitive to the fuel parameters. And so therefore, you have to be able to understand what the fuel is going to do. So that's what we're going to try to do. So we're going to teach you about how to do fuel chemistry. As we showed last time, I hope you got the idea. The fuel chemistry is pretty tricky. So it's definitely not Arrhenius single step. It's got not always monotonic behavior. Once you combine several reactions, you've got to be pretty good to figure out what's going to happen next. And so we really get into a lot of numerical simulations of the complicated reacting systems to understand them. And the details really matter to understand why the fuels behave differently. So, for example, most of the fuels we use today are not that different. They all have energy densities within a range of about a factor of 2. They're all made of hydrogen, carbon, and oxygen. They have volatility, evaporation, all about the same range. They basically, to the point of view of a mechanical engineer, probably the same thing, right? Fuel. And yet they actually have quite different octane numbers, cetane numbers, propensity to make emissions. And so they really are different. And it's due to details, the main properties are about the same, but the details are different enough that you need to worry about it. And so that's what we're going to do today. Now, what I'm going to tell you about today is general. It's not just for combustion. So there's all kinds of kinetics problems in the world and thermochemical problems. And all these things I'm going to tell you today are basically applicable to all of them, but I'm going to focus mostly on the ones relevant to the combustion. What else? Yeah, so we're going to try to understand. We talked a lot about experiments last time. Most of the rest of the lectures, we're going to talk mostly about, primarily about the theoretical methods and computational methods, which are taking over, really, because the experiments are difficult to do and the computations get faster and faster as the computers improve. All right, so here we go. What's our plan of attack? First, we're going to talk about thermodynamics and thermochemistry and some equilibrium statistical mechanics. Then we'll do rate theory. We'll start out by doing conventional transition state theory, which is still the mainstream way to do this. And we'll focus on the high pressure limit, which means we assume perfect thermalization to start with. Then we'll get fancier, talk about variational transition state theory and pressure dependence of rate coefficients. We may not get into this till tomorrow, depending how fast I go. And then a little bit later in the week, we're going to talk about mechanisms and how you can construct the complicated mechanisms and how you handle the complicated mechanisms. All right, so the reason why we're starting with thermo is that the whole purpose of kinetics is to get to equilibrium. So the kinetics is, all the chemistry is going towards equilibrium. And if you don't know where you're going, you're not going to get there. So it's good to know where you're going, and you can just figure that out right from the beginning with thermochemistry. And then we'll worry about how fast we get there a little bit later. Now, there's a big part of thermodynamics that's about phase behavior of mixtures. So things like volatility, miscibility of liquids, stuff like that. I'm not going to talk too much about that, but it's definitely an important thing. And then I'm going to talk mostly about what we call thermochemistry, which is about reactions. It's about the heat of reaction, the entropies of reaction, equilibria. So the first law, thermochemistry, gives you the energy density of a fuel, the final temperature you'll achieve if you burn all the fuel. The second law is related to the detailed balance, and so it gives you the reverse rate coefficients. It also tells you the final composition at equilibrium. It's related to the equilibria. And so this is our main topic, but I'll just talk very briefly about these. All right, so this is kind of typical of how the density, the boiling point, and the melting points of different fuel molecules change with temperature. So you can see the density doesn't change too much. It increases a little bit as the number of carbon atoms increases. And the boiling point increases a lot as the molecules get heavier, and the melting point increases a little bit. So this is for straight chain alkanes, and the other hydrocarbons are all kind of similar to this. So that's the first thing. When you get to really large molecules out past the diesel range, what happens is that the molecules pyrolyze at lower temperatures than they boil. So you can't just take, say, you take some oil out of the ground, you can boil it, and you'll make a lot of the oil will evaporate and go to gas phase. And you can take that, and that'll become gasoline and diesel and jet fuel. But then you'll still have about half the barrel of liquid that didn't boil. You can increase the temperature to try to make it boil, but actually what happens is it starts to react in the pot. And you'll actually make into eventually a giant lump of Coke. The whole thing will turn into a solid, horrible black mess. Now, to try to beat that, you can do what's called vacuum distillation, where you lower the pressure by vacuum pumps, and then you can get it to evaporate at lower temperatures where the reactions don't start. And so that's what they do. So if you look in a refinery, first they have what's called the atmospheric still, where they take off all the molecules that are normal fuels right from the beginning. Then they have a vacuum still, where they take off things that won't boil at regular temperature without reacting. Then after they do that, they have stuff that won't even come off in the vacuum still, and they call that residual. It's the stuff that's left in the bottom of the barrel, the bottom of the still after they try to boil it, even under vacuum. And that stuff, a lot of that ends up as like asphalt to make shingles on roofs, stuff like that. It's a lot of it's completely useless, actually.
What's the highest number of carbons that they can get something useful out of?
The fuels that we use typically are maybe 30, 35 carbons is the end of the diesel range. Sometimes they can take a little bit of the heavier molecules and sneak them in, and dissolve them into the regular fuels. And if you just put a little bit in, you won't notice it. But if you put too much in, you'll start making a lot of soot when you burn it, because the stuff, you have enough of it that it'll stick together. And in fact, it may not even dissolve. So some of the molecules form emulsions, where the heavy molecules just stick to each other. And even if you put them into the fuel, they still stick together. So they'll make the whole fuel cloudy. And usually that's bad. Usually they'll clog your filter and have a lot of troubles. But they do it anyway, because you had these heavy molecules in the refinery. Okay, so this is a fun thing about refinery science. You run a refinery. Suppose you buy 100,000 barrels of oil per day. That's a moderately big refinery. You have 100,000 barrels of oil. At the end of the day, you have to process them all, because the next day you're going to another 100,000 barrels. And you don't have enough tanks to hold many hundred thousands of barrels of oil. So every single thing that comes in, you have to do something with it. Okay? Now, you could pay somebody to haul some of it away as toxic waste, but then you're not going to make any profit, because the cost of the waste is so high. So you have to be able to not only do something with it, you have to make it something that you can call a product. Now, it could be a product you could sell for a very, very low price, but it has to be a saleable product. It cannot be a waste. If it's a waste, it'll be regulated as a waste, and you'll be bankrupt. So you basically have to take every molecule that came in, those 100,000 barrels. That's a lot of molecules. And you got to get every single one of them, and some customers got to buy it at the end, at the end of the day. So this is a really interesting optimization problem. So you really want to get that valuable jet fuel and diesel fuel and gasoline. So you love to buy those oil because it's got lots of those molecules in it, but it comes with a bunch of doozies. The molecules are not worth much at all. And so a lot of the cleverness of a refinery is trying to figure out what the heck to do with these gigantic molecules that won't do much. And they end up, a lot of them is like asphalt, road tar. Some of them end up as petroleum coke. Some of them you can make into a kind of coke that's good for making high quality steels or for making aluminum electrodes, stuff like that. But some of it, you're in trouble. And so they end up shipping away to countries with poor, not very strong environmental laws, some coke that's sort of like coal, but was made from petroleum, but it's got all heavy metals and sulfur, and it's really not a really very good fuel. And so then as the environmental regulations improve, they get squeezed more and more. It's like get stuck more and more with these different things that they don't know what to do with. And it might not be that much. It might be 0.1% of how much you bought, but that could still be 100 barrels a day. If you have 100 barrels a day of something you cannot get rid of, it builds up, and your tanks will be full pretty soon. By the end of the month, you have a heck of a lot of material to get rid of that's completely useless. So anyway, that's a challenge. But anyway, that's part of the reason why they have a slogan that says, "Dilution is the solution." So if you have some bad thing and you don't know what to do with it, you're selling a lot of gasoline, so maybe just put a little tiny bit in there, each little bit of gasoline, and maybe nobody will notice. It's just diluted in there. And so that's the common thing to do. And you have a refinery. Suppose you have an upset, like a pipe breaks, and you have to shut down one of your units. All of a sudden, the whole thing's out of whack, and you end up with stuff that's off spec. You end up with a batch of gasoline that doesn't meet the gasoline specs, say. Now you have, your tank is full of the stuff that you can't sell. So you got to figure out what am I going to do with it, right? So again, you try to does my buddy at the next refinery, can he take a little bit of it and they'll dilute it into his gasoline or something like that? And won't wreck up it. He's far enough from the spec that he can manage to have it. Anyway, that's that. So if you ever see a chemical engineer and you wonder why they get paid the big salary, it's they're dealing with problems like this. All right. Volatility and solvation. So there's a big part of thermodynamics, which I call thermophysical properties, but I'm not sure if that's what everyone calls it. And that's about phase behavior. For combustion, we really care it's about how the liquid fuel evaporates in the engine. And that's very critical for things like diesel engines, where you really want to know what fuel-air mixture are you creating with your fuel injector. And also in gasoline engines, too, you have to make sure that the gasoline is going to evaporate in the intake port and not come in dripping into the cylinder as liquid, for example. Another where this comes up is on the back end. So coming out of the tailpipe, we have some hydrocarbons. Remember I said yesterday that a couple percent of, say, gasoline comes straight through the engine, unburned, and goes into the air. And so that stuff actually does photochemical reactions in the atmosphere. It's partially oxidized and gets polar enough that it can stick to it. The molecules will stick to each other. And once that happens, you can actually form an aerosol. The phase equilibrium would favor those molecules, instead of being free in the gas phase, actually sticking together. And that makes the haze, photochemical smog haze that you see, is from the formation of those aerosols. And exactly understanding how that happens is very complicated, but a big part of it is understanding the phase diagram of you have air, water, dissolved, partially oxidized organics of various sizes, and what's the phase diagram of which of that stuff wants to be in a condensed phase compared to what being in the gas phase. Distillation, this is historically a very big deal, was trying to figure out how to run the distillations at the refineries. A high fraction of the energy that's consumed at refineries just running the distillation. It's a lot of capital cost too. And so people spend a lot of time on this. I think this is now pretty well understood because they worked on it so hard. But it's actually quite complicated. You have certain mixtures you can't separate with a normal distillation. And so the people had to work out special ways to handle that. You have all kinds of funny things happen in the phase diagrams. And then miscibility. So sometimes you have two liquids that are not miscible. They form two different phases, like oil and water, oil and vinegar in your salad dressing. And when that happens, the important one for us is water and fuel. So usually hydrocarbon fuels don't dissolve very much in water, and you get two phases. So if, for example, you have water leak into your tank, either of your car or a refinery tank, the water typically would sit on the bottom and the oil would sit on top. But some of the oil molecules dissolve into the water. The same thing happens in the ground. If you spill some oil in the ground, mostly it sits there as a puddle of hydrocarbon. But if it rains, some of the hydrocarbon molecules will dissolve into the water and will get carried down into the groundwater with the water as it flows through. And then they might show up in somebody's well a mile away. And then you might get sued because you polluted the guy's well. So understanding this is very important for environmental engineering. You definitely don't want phase separations to occur in your fuel tank or fuel injectors. It can lead to all kinds of problems, fouling and different things like that. And then the volatility, very important thing to know about the volatility. For the first gas, you can use a boiling point to understand when things will evaporate. But remember, the boiling point is a funny thing. It's just when the sum of all the partial pressures of all the components in a mixture equals atmospheric pressure. It's not really a very fundamental thing at all. And it's not, if you just look up pure compound boiling points, they're not really directly related to the Henry loss constant. And this is particularly if you have, for example, you had a little bit of organic dissolved in the water, the Henry loss constant of that hydrocarbon in the water can be a lot different than what it would have been if that hydrocarbon was in hydrocarbon, because the interactions of hydrocarbon in water and hydrocarbons are really different. So the boiling point is not always a reliable way to judge vapor pressures. But there's theories for all this, and there's a whole community that has its own conferences and writes its own journals and stuff. It's all about trying to figure out the thermodynamics of the mixtures. I'm not going to say anything else about it for the rest of this week. All I'm going to worry about is heat release. So heat release and combustion, it's going to depend on enthalpies and heat capacities. I'm going to care about equilibrium constants for reactions, so we can get the forward and reverse rates related. So we're going to need enthalpies, entropies, heat capacities. And so we're going to look in the thermodynamics and StatMech focused on the thermochemistry problems. And where do we get the numbers? How do we measure them? A very new method for doing this, which is really great, I'll tell you about. And then how we represent the data so we can use it in our computer models. All right, so here's some basics of thermo. You guys all know that the enthalpy is the energy plus P delta V. And then you can compute the enthalpy of a reaction, which is the difference of the enthalpies of the products minus the reactants. You can see how it changes with temperature. It depends on the heat capacities of all the species. This is all for ideal gas mixture, which is usually good enough for our purposes. Then you want to know the free energy, because the free energy is related to the equilibrium constant, involves the entropy as well as the enthalpy. And then we could finally get back to the equilibrium constant. And for the typical standard state that's used in gas phase, it's almost always 1 atmosphere is the standard state. So that's the P naught. And so it's just the partial pressure of all the species in atmospheres is what these guys are. And that's the normal equilibrium constant. This is dimensionless.
What do you mean by for surface sites use fractional occupation?
Yeah, so if you're doing a catalytic problem, you have to figure what is the activity. And so for a catalytic heterogeneous catalyst problem, it's the fractional occupancies, like the number of active sites you have in the surface of the catalyst, what fraction are occupied by a certain species. That fraction is like theta. The theta 0 is like all the sites, and that's the theta divided by the theta 0.
Is it dependent on temperature as well?
I'm sure. So yeah, so as you increase the temperature, less of the things will stick to the active sites. They'll be emptier. And as the temperature goes down, they'll all get full. Okay. Yeah. If you do get into trying to do kinetic models on heterogeneous catalyst, I recommend that you read some papers first. It's very confusing because of the standard states and how you handle the fact that there's like only a finite number of sites. It's not really exactly the same as the gases. Some species on the surface can move, so they act sort of like a gas, like a two-dimensional gas. But a lot of species just bind to particular sites, and so you have to treat them a different way. But anyway, there's some nice papers and some textbooks that explain this. But some of the literature is kind of confused and might confuse you also if you read it, so look around. But I'm not going to talk about that either. All right, standard enthalpy of formation. You start from the elements in their standard states, and you make a reaction that creates the species. So if I want the standard state of enthalpy of formation of methane, I do this reaction, carbon with hydrogen. These are the standard states. Carbon solid, graphite, and hydrogen gas are the standard states. And I compute the delta H for this, or I measure it if I can do that reaction. And that number is what's defined to be the standard state enthalpy formation of methane. And the standard state enthalpies of formation of all the elements in their standard states are defined to be 0. Now, the fact that the carbon is a solid in a standard state but everything else we're doing is ideal gases. This is another situation prone to student error in journal papers and textbooks. So just watch out. Professor error, too. All right, so how do we do the computations? As a t-dependence, the enthalpy is the enthalpy at, say, your standard state temperature, or your temperature that you measured at. If you know the enthalpy at one temperature, you want to compute it at a different temperature, you do this integral of the heat capacity from the one temperature to the other. And that's the enthalpy. This is the heat capacity at constant pressure. There's another one, CV, at constant volume. They're a little bit different. If you take the CP, you can also use that to compute how the entropy changes. So if you know the entropy at some temperature, you can compute the entropy at the other temperatures as long as you know the heat capacity function. Then once you know these two guys, you can put them together to get the standard state free energy. And then once you know the standard state free energy, you know the equilibrium constant. Notice none of these things depend on the pressure because all of these are defined for the standard state. So the standard state is sort of set the pressure to be 1 atmosphere. And so equilibrium constants, as these dimensionless ones like this, do not depend on the pressure at all. Okay. But they do depend on the temperature. If you have non-idealities, suppose you have very high pressure in your super fancy diesel engine, you might worry about the fact that it's not an ideal gas anymore. That non-ideality actually comes back here, that these activity coefficients are not exactly. So for ideal gases, the activity coefficient is the partial pressure. But for a non-ideal gas, the activity coefficient is actually different than this. So it's like this for low pressures, but as you increase the pressure, it changes. And then if you want to compute that, there's things like the Peng-Robinson equation of state that people can use to extrapolate to higher pressures. That works pretty well. What else? Heat capacities. There's several different formats that people use to express these. I don't know why. For historical reasons, there's several ones. So NIST and Benson, who was a very important guy in this field, they tabulated CPs at some particular temperature values. So just some, 500 Kelvin, they would tell you what the heat capacity was there. 800 Kelvin, tell you what it was there. 1,000 Kelvin, tell you what was there. So you can look up and find tables that have heat capacity at a couple different points. So that's one way to represent it. Then a bunch of people tried to take these kind of points and fit them to polynomial fits. And so there's at least 4 different fits of this type that I'm aware of. One called Showmate, which is used by NIST on their website sometimes. One called Wilhoit, which I think actually is a form that provides really good quality fits because it's very similar to the actual behavior of heat capacities. However, unfortunately, poor Mr. Wilhoit had a typo in his first paper where he presented the polynomials. And so then after that, the equations were not consistent in the paper. And so it caused massive confusion. And I think most people then decided, let's not use them. They didn't understand what the problem was. And they just said, forget it. So the Wilhoit's never really caught on. But I would say if you want to have a really good fitting form, this is a good form. And then NASA, in the JANF tables, the format they use really caught on. And so that's what you'll find mostly in combustion codes because it was so influenced. The combustion community was influenced very much by NASA, particularly the Apollo project and the early rocket projects provided a lot of funding to do research on thermochemistry. Now, unfortunately, the NASA form is not very good. And so the people then messed with it. And so there's 2 different NASA forms, the original one and the slightly modified one. They look kind of the same. And they're big tables of numbers that are like polynomial coefficients. And I think if you count the numbers, you realize they're not exactly the same because they have different numbers of coefficients. But if you just look at it by eye, you might think one is the one and one's the other. It's really confusing. And also, the NASA form, they couldn't get a good fit with the polynomial form, so then they did it as 2 polynomials, and they tried to make the 2 polynomials match up at one temperature. But for some reason, I don't understand, sometimes when you look in the data, they don't actually match. There's like a kink at the splice temperature. And so the heat capacity then from the derivative would be like infinity or something. Anyway, just give you some warning of the problems you're likely to get into, and just don't be upset. And of course, there's typos and stuff like that. Anyway, science is a human activity, and so it has problems, just like all other human activities. And then the heat capacity, for certain kinds of molecules, there's a very good theoretical basis for how the heat capacity should change with temperature, which is not a polynomial form. It's a pretty complicated form. I'm going to show you in a little bit. So if you happen to know the fundamental information, you could just use that form, and that will provide a much better fit because it's actually theoretically correct. These other things are like just polynomial kind of attempts to fit something that's not really a polynomial. Does that make sense? All right, so this is the kind of thing, if you look up in tables, what you'll see. So you'll see the enthalpy of formation, the entropy of formation, and then the heat capacity at a couple different temperatures. And this is a very common. There's about half the literature uses in joules and half does in calories, just to make it confusing. But fortunately, they differ by a factor of 4, so that's big enough that usually you can tell which one's which. And a lot of people give too many decimal points. Look at these, So there's no way that anybody knows 5 decimal points on a heat capacity to 1,000 Kelvin of anything. So this is just baloney. So this is normal, right? Just like if you ask your students to do a homework problem, they'll give you as many decimal points as the calculator that they have gives, right?
How many would you say are reliable?
Well, a lot of, I don't know. A lot of these are calculated. If they're calculated, these days you can calculate to like 1 or 2 in the ones place, plus or minus 1 or plus. Actually, this is joules, so it'd be plus or minus 5 or plus or minus 10. Okay. So this would actually be way off. And like for solid graphite, who knows what it really is. So this might only be good to one significant figure, possibly. Maybe somebody's done a better job. I don't know. At 2,500, I'm sure, just one significant figure. So this is ridiculous. For these guys, like benzene, so maybe you're uncertain by 2 units there, so it's maybe to 1%. It's still pretty good, but it's definitely not 6 significant figures. It might be 3. All right. This is more databases. These are different websites. You have them in your book there that you can look up and have lots of tables of data. And they typically look something like this. This is the GenF form. So you have the name of the molecule, some code which is supposed to tell you where the numbers came from. It's definitely worthwhile for you to figure out the code so you know what the heck, if you should believe the numbers or not. Then they'll have the formula of how many carbons and hydrogens and oxygens. You have to know the formula, the rules. What phase it is a G. And then these are the temperature ranges for the polynomial fits, the low temperature fit and the high temperature fit. They're going to splice together. And then these coefficients for the high temperature fit, and here's for the low temperature fit. Notice the high temperature fit comes first before the low temperature fit. You can imagine the number of mistakes are with this. But anyway, if you plot what you think it is, you'll see if it's crazy, if it has like wild discontinuity in the middle or something. You'll know you did it backwards. And then the nice thing about polynomials is we know how to integrate them. So the integrals that you need to do to get the temperature-dependent entropy and enthalpy, you can do them analytically. And so here they are. So if you know the CP is this form, then this is going to be the form for the entropy and for the enthalpy. And those are exact. So they do the analytical integrals for you. We really care a lot about the heating value of the fuel, right? Because energy density is one of the greatest things about fuels. And so you have to worry about what someone's telling you when they tell you efficiency. They can either use the lower heating value or the upper heating value for the fuel. And it can change the efficiency numbers a lot because they're really pretty different. And so the lower heating value assumes that all the water that's formed is in the form of steam as a gas. And so for a typical car, for example, this is pretty accurate. That coming out the tailpipe, you have a lot of steam. You don't have liquid water pouring out usually. And so you should use the lower heating value. The upper heating value is what you would get from using the heat of formation, because the standard state of water is liquid, not gas. So if people just reported the heat of formation of something, they might, that a reaction that involves water, they might use water, use its standard state, and then they would get some number of enthalpy change that would correspond to the upper heating value. Also, if you do a bomb calorimetry experiment, usually you do is you burn the stuff, you have it sitting like in ice. The heat from burning melts the ice. You measure how much ice melted. And the whole thing at the end is at room temperature or the ice temperature. And so at the end, all the water that was formed from the reaction is going to be liquid phase. So you'll measure the upper heating value is the direct measurement from heated combustion measurements. But in the operation of the engine, usually what you want is the lower heating value. So again, this is another one to just watch out for. And again, if somebody reports something that seems like a wildly unbelievable efficiency number, then they might have used the upper heating value instead of the lower heating value or vice versa to make their number look better. Or maybe just not even being aware of what they're doing. But this causes a lot of problems in literature too. All right. A very useful thing to compute right away when you're doing a fuel problem is the adiabatic flame temperature. So that's to compute, assuming that the reaction ran, say, to completion, then you can compute what the heat of combustion should be, divided by the heat capacity of your system, and you get the temperature rise, is the delta H over the Cp. And then that'll tell you, you start at room temperature, what temperature should you get to? And it's pretty important, just for safety, if no other reason, to know what your adiabatic flame temperature is. And that's sort of the maximum temperature that could possibly be achieved. In reality, your system usually has heat losses, so the real temperature is a little bit lower. But this is a good number to know before you start. And so you can see these are the adiabatic flame temperatures as a function of the equivalence ratio of, so over here is fuel rich, here's fuel lean, and stoichiometric or near stoichiometric is where you get the peak. And these are the different fuels. And you can see that they have similar, but not exactly the same adiabatic flame temperatures. And when you're trying to compare, oftentimes you have an alternative fuel. You're trying to compare your alternative fuel to a regular fuel. It's a problem because if you make a flame of your fuel, typically it would have a different adiabatic flame temperature than the fuel you're comparing to. And so the whole temperature profile will be slightly shifted. And so all the rates will be different. And so then trying to make a one-to-one apples-to-apples comparison is pretty tricky to do. And so sometimes people do is add a little bit of diluent or something to try to make the adiabatic flame temperatures the same for the two fuels they're comparing. And that removes sort of the biggest effect of the temperature. The adiabatic flame temperature, one reason why the adiabatic flame temperature is an overestimate is that oftentimes when people compute it, they don't consider equilibrium. And one equilibrium in particular is very important, is that if you assume that all the carbon burns to CO2, it's not really true. Actually, some of the CO will be left. So you can see here that, particularly at low pressures, the CO is like a factor of 5 less than CO2, but it's not 0. It's pretty much. So you have quite a lot of CO2 left and CO left, and actually you have quite a lot of O2 left as well. And this is observed all the time. Whenever you do an experiment with combustion, it was surprising to me when I first saw this. You actually have oxygen coming through the flame. Unless you're quite rich, because of this equilibrium problem that you can't burn the CO all the way to the CO2. And this varies a little bit with pressure. So if you're at high pressures, this is not such a big deal, because then the CO will be more than an order of magnitude down from the CO2. But at low pressures, it's quite a lot of the stuff. Also, you typically will have radicals formed, and oftentimes their kinetics of recombination is slow. So they'll still be in the form of radicals, which means that they have like a heat of reaction available for them to recombine that would release a lot of energy, but that might not be released until way later, way downstream before you made the measurements. So the temperature in the flame might be a lot lower than you thought it should be. Okay, standard entropy. The way this is done is you assume that the entropy is 0 at absolute 0 Kelvin. And then you just integrate Cp over T all the way up. And if someone has done a very nice calorimetry experiment down from low temperatures up, you can just use the experimental heat capacities and do the integral and get a very good number for the entropy. Anyway, that's the way that it can be done experimentally. And so for some stable molecules, people have done this. The calorimeters have been hard at work, and so you can get that. But a lot of our molecules, we actually compute it using statistical mechanics, and I'll talk about that in a little bit, instead of doing the measurements. And particularly for things like free radicals and reactive intermediates, you can't do this calorimetry experiment very easily, because you can't make a gram of the reactive intermediate and stick it in a calorimeter. So you have to do it some other way. So we do it with computation usually. OK, so here's some basics of statistical mechanics. How many of you have ever taken statistical mechanics? OK, so the rest of you can ask questions to those guys. Right, hold on. All right, so there's a quantity. Well, let me start by explaining. What's different between two different materials when from considering a thermodynamics point of view? What's really different between them is that there's different energy states are possible. So if I have a beaker A and a beaker B, and they have a different heat capacity, the reason they have a different heat capacity is because the materials actually have different energy states available. And so these energy states are the critical quantity. And it turns out that this particular sum of the energy states in exponentials, this thing turns out to be enough to tell you everything about the normal equilibrium thermodynamics of a material. And this thing has a special name called the partition function, which has nothing to do with the partition function that's involved in vapor-liquid equilibrium calculations. I don't know why they use the same word. Actually, it was, I think, a guy named, it was here, no, it was at Yale. It was Gibbs, right? He's the guy who invented all this terminology for these functions. Anyway, so for example, the Helmholtz-free energy, which is U minus TS, or G minus PV, that's just the logarithm of this partition function times Boltzmann's constant times temperature. So it's pretty amazing. So if I know what this Q is, if I know the energy levels that are possible, I add them up this way, I put it in there, I get a number, and that number turns out to be the Helmholtz-free energy of the system. It's kind of cool. The energy of the system turns out to be the derivative of the logarithm of this Q thing, the temperature with that thing in front. Okay? And some of these are pretty straightforward to compute. Like this one, I think, if you just do that here, you'll see what you're doing is getting a Boltzmann average of the energy, which is what you'd expect the energy to be. All right, so most of the motions that we have in molecules and in solids and in liquids are vibrations, molecular vibrations. There's a lot of chemical bonds. Each chemical bond has a vibration. Each bending motion of each bond also has vibration because they're all vibrating. And all those vibrations provide most of the energy states and most of the possibilities of what can happen when I put some energy in a molecule, it's mostly making the molecules vibrate. And so I can calculate the energies here that correspond to the vibration using harmonic oscillator approximation. And people do this even if it's not accurate because it's really simple. It gives you really nice analytical formulas. Very convenient. So people do it all the time. We know, of course, the molecules are not perfect harmonic oscillators with parabolic potentials. They have more complicated potentials. But anyway, you can do it really easily. This has an analytical solution of the quantum mechanical problem. So you know all the quantum mechanical energies. And then you can actually calculate the Q for the vibrations. It's just you multiply this funny function with every different normal mode vibrational frequency of the system in there. And just evaluate that thing. And that number turns out to be the Q vib. And that's most of what Q is, because most of the motions are vibration. But we also have some translation. So for translations, the energy levels are known to be this. And the corresponding partition function, if you put them in the exponent and add them all up, is this. This summation does not have a simple solution. However, the energy levels are very closely spaced, and if you approximate the sum as an integral, that integral can be evaluated analytically. And this is the value of the integral. So the Q is approximately this thing here. And it gets proportional to the volume, and it gives this temperature to 3/2 power, and it has to do with the mass. And that's it. The rotational partition function looks very similar. Instead of having mass, now it has the moment of inertia in there. If you have a nonlinear molecule, there'll be 3 different moments of inertia for a solid material. And you just multiply the 3 of them together, take the square root, and put it in there instead of the I. And then you get the rate formula. And you get an extra factor of pi to the 1/2 just to make all your numbers a little bit off, because you forget the pi to the 1/2 in your calculation. All right. So now we can write down the total partition function, which is what we needed to compute the thermodynamic properties. And you just multiply the vibration times the translation times the rotation times an extra one that's for the electronic motions. The electronic thing is usually 1 for normal molecules. It's 2 for most radicals. And there's a couple of goofball molecules that have low-lying, non-degenerate electronic states. And those you have to do some special little calculation.
Are there any additional ones that you would consider when doing spectroscopy measurements?
Any other motions?
Any other partition functions that you need to include in your total partition function?
This is all you need. You could actually have nuclear spin. The thing that causes NMR is due to nuclear spin states. There is a partition function for that. It turns out that in the reactions and stuff, that thing hardly ever changes at all.
Okay. So
usually people would forget it. But basically, you need it for every degree of freedom. Everything that can be different about the molecule to give you an energy state, you should put it in. And again, typically the vibration one is dominant and the important one to figure out. And it's different for different molecules because every molecule has different fundamental vibrational frequencies. Whereas the other ones, like the translation, is just the mass times the temperature to 3/2 power. Everything's got mass. The masses don't change that much, so it's not such a big factor. All right, and so those Qs I told you were each for one molecule. But in the real system, you have a lot of molecules, n molecules. And the real partition function should be this whole product to the nth power divided by n factorial. The n factorial comes to the fact that the molecules are indistinguishable in a quantum mechanical sense. That if I flip 2 of them that are identical molecules, I can't tell. Because from the point of view of quantum mechanics, those nuclei are exactly the same. They don't have serial numbers on them. They're not colored any different color. All carbon atoms are carbon atoms. That's it. And so to correct for that, you have this n factorial. The logarithm of Q, which comes into a lot of those formulas I showed you, is then n times the logarithm of this molecule thing minus n ln n from the Stirling's approximation on the logarithm of a factorial. And you can rearrange this and write it this way. Ln Q is equal to n ln Q, where this is the same Q except that the Q trans was changed by making it V over n. So it's sort of like the volume per molecule. And if you have a non-ideal gas, you can actually correct the Q with the equation of state. It's not very hard to do. It doesn't make a big effect. In liquids, it does make a big effect. The free volume that the molecules have to move in the liquid is much smaller than the total volume, because a lot of the volume is excluded by the other molecules of the liquid. So then you don't really have to worry about it. But the vibrational part, which is the biggest one, is not really affected, because the vibrational frequencies in the liquid phase are not really that different than the vibrational frequencies in the gas phase. So the number is almost the same. All right, so then you can compute it. So if you look in the NIST webbook, this website, and you look in a molecule, it'll tell you what the recommended value is for the heat of formation of the enthalpy, the recommended value for the entropy. It tells you the units. It tells you where to look up the reference. It told you how they figured this out. These guys, the NIST guys are good. They usually try to have real error bars. And then they'll also tell you, if you look into it, how they computed things. In this case, for methane, is this methane? Yeah. People have actually observed in the infrared and the Raman all the different vibrational frequencies. So the vibrational frequencies are from experiment, so that makes them pretty accurate. And so, and they'll have a discussion about, sometimes the two measurements in the infrared and the Raman disagree with each other, and then they'll have a little comment explain which one they selected to use to make the thing. They'll have a rating. If it's a rated A, it means they're pretty darn sure it's right. Rating C means there's some problem. So maybe you look in the spectrum, there's some problem about maybe the band is broad and they're not sure exactly what the frequency is or something like that. So, so that's how you would do it. So if you know the frequencies, you know the mass, you have to know the moment of inertia. You can get that actually from microwave spectroscopy. You know all those quantities. Now you can compute the entropy, you can compute the heat capacity, you can compute the enthalpy perfectly, except for the base enthalpy of formation. You have to get that from a calorimetry experiment. Everything else you can compute. However, methane's nice because it's a rigid molecule, but a lot of the molecules we care about are not rigid. They have floppy motions that you can rotate around some CC single bonds, for example, in the molecule. And the floppy motions are definitely not represented well by a parabolic potential. They're not just small amplitude vibrations. They're actually flopping around, swinging the molecule this way and that, with big long tails wiggling around. And so the partition function formulas are not accurate because it's for a harmonic oscillator only. And so the rotations, puckering of five-membered rings, some umbrella vibrations, and the entropy values that are in the table, if you read it carefully, they'll tell you it was not from experiment. Usually they're not from experiment. Usually they're from calculation with StatMech formulas. And if they use the harmonic oscillator approximation there, that means that number is not right. So don't believe it. Just because it's in the table does not mean it's true. Okay? It could be true. Now, if you read it carefully, they'll tell you the error bar, and they'll tell you what why they think the error bar was what it is, and usually they're pretty good. But you have to read it. If you just see the number, grab the number with your cut and paste program, stick it into your calculation, and then you wonder why you have big errors in your predictions, well, serves you right? I mean, they warned you. They had a big error bar on it. They probably had some low footnote. There's a dispute about this number, something like that. So I would say always read the error bars. And the NIST guys have a saying about this. They say, we give numbers for free. All values of all numbers are free, but we charge for error bars. Okay, because error bars is a lot harder to figure out what the error bar is. And if you don't know what the error bar is, what good's a number, right? All right. And particularly, a lot of the thermochemistry stuff is from 1950s, 60s, JANF tables from guys building rockets. They did the best job they could, but they were in a hurry, right? They were in a program. They were building rockets. Their job was not to be the world's best, calorimetry guy. It was not their purpose. Their purpose was to make a rocket that worked. So they got a number that was good enough for their purpose. It doesn't mean that might be good enough for your purpose. And a lot of those numbers have propagated through. So those tables are still, they were initially populated by the JANF project back in 1960 or whenever it was. And so, since then, some of them have been updated and checked carefully and are really great. And some of them are still the number from 1950. If you look at the footnote, it'll say, suggested estimate from a private communication with Joe Smith, April 4th, 1952. So maybe Joe Smith was great, and he told you the great number, but he didn't say what method he used. He didn't give an error bar. Suggested, the guy walked down the hall and said, "Hey Joe, what do you think this number is?" "Oh, it's about 17." "Okay." They had to build a rocket. They didn't have time to mess with all the numbers, and so all right. And then also, oftentimes it's impossible to measure all the vibrational frequencies. So for methane, they know them all. But if you do infrared spectroscopy, any of you guys ever do this? You get a spectrum. It has a lot of peaks in it. But then if you calculate, you can calculate that it should be 3n minus 6 vibrational frequencies. Oftentimes, there's not 3n minus 6 distinct bands. And the problem is that one of the bands is overlapped with another one, so you can't see it. Or else you have one of them has the intensity is too low, and it's in your noise of your detector. Some of the bands are forbidden. That means they don't have dipole transitions. So they don't show at all in the regular infrared spectrum, and you have to do Raman experiments. So Raman experiments have a much worse signal to noise. So you still may not be able to see it. Could be an interference from atmospheric water vapor, which is everywhere. So there's a lot of reasons why they won't see all the lines. So what's been happening recently is people started using quantum chemistry to fill in the gaps. So the way this works, I'll talk a little bit more about this in a few minutes, but you calculate the second derivative of the potential surface. So it's sort of like there's a bond. It's like a spring. You're trying to figure out the vibration. So you need the spring constant. So that's related to the second derivative of the potential as you move the atoms around. So if you know all the second derivatives, you can actually calculate it by doing normal mode analysis, just like you guys probably did in physics when you were in high school or something. And these things are now pretty easy to calculate. The people have written some nice programs that calculate these approximately using different approximations of the quantum mechanics, of the full quantum mechanical method of calculating the energies. And once you have these numbers, which are approximates, they have some error bars, but assuming that they're right, you can go ahead and do the normal mode analysis. It's perfectly easy to do, and then you get the frequencies. And then you plug them into the stat mech formula I told you before, and now you have all the thermo. So, but keep in mind, it's really hard, in fact, it's impossible almost, to compute the V exactly for multi-electron molecules. And so people, there's a whole community called the quantum chemistry community, and all they do is try to figure out better methods to better approximations to get more and more accurate V's and more accurate of these things. And you'll see an alphabet soup of different approximate methods, B3LIP, CCSD, CASPD2, MRCI, HF. These are all acronyms for approximations for solving the electronic structure problem to compute V. And you don't need to understand anything about it. All you do is you buy the program, you type in B3LIP, go, and they'll tell you. And then you can type in a different program, type in HF, go. And they'll each give you a different second derivative. So they'll give you different numbers for this matrix. And when you solve it, you get different frequencies. So it's an approximate method. So each different approximation will give you slightly different. All right. Now, you might hope that you could just do a sequence of better and better approximations. It'll converge to the true value, and you'd know what it was. But it's not that good. So they have the approximations have systematic errors which are not compensated for by any method. They have some sequences you can do to kind of converge something, but it's only converged to some level, and then you have to do some other thing. So the field is sort of still working. That's why there's all these different methods are still competing with each other, because people are all trying different approximations. Currently, most people use different varieties of density functional theory to do these second derivative calculations, and it's pretty good. And so you'll see a lot of papers use MO8, MO6, B3LIP. There's a couple other ones, and those are all different approximations for doing this calculation. They'll all give you something slightly different.
When you say slightly, is it like 3% or like 20%?
Usually, it's like 3%, but sometimes it might be like 100%. Yeah. And so that leads to this. So there is a database called the Computational Chemistry Comparison and Benchmark Database, where they try all the different approximations for calculating all this stuff. And then wherever there's experimental data available, like the real observed vibrational frequencies, they try to show them too. And then you can get an idea of how accurate things are. And for most molecules that are normal, most of the methods work pretty darn good, which is why they're famous methods. Because if they worked terribly for some normal molecule, everybody would say, why use a stupid method? And you wouldn't hear about it. So the ones you hear about are ones that work pretty well. But if you get some wacko reactive intermediate, and there's like no experimental data, and so then nobody knows what the real answer is, and all the methods predict something different, who knows what the real number is? And some of them, eventually somebody does an experiment and shows what the real number, and it's way off from all the methods. And then those are, in this database, there's a thing called the sick molecule list. Their molecules, it's not that the molecule is sick, but the computational methods are sick for this molecule. They can't, for some reason, they miscompute it. But most molecules, they compute correctly, and most quantities, they compute correctly. But every once in a while, you hit one that they don't. So this is a fun database to take a look at. If we have time at the end, I can pull it up. You can take a look and see. So this just gives you an idea. So this is a Hartree-Fock. This was a method that was very popular until about 1990. It was the main method that was used. And you can have a comparison. These are the experimental frequencies of methane vibrations, and these are the calculated. And you can see this one, it's off, but it's got like 2 significant figures. This one is pretty darn great. This one is off by more, but still not too terrible, still 2 significant figures. And this one is also 2 significant figures. So it's okay. And so this was the most popular way to do this as of 1990. Since then, they've invented density functional methods, which are better usually, but not always. So this gets into radicals. So as I said, the most important reactions in combustion all involve radicals, free radical intermediates, reactive intermediates. And problem with them is you cannot do Baum calorimetry or any kind of calorimetry on radicals, because you can only make 10 to the minus 7th moles per cc of them, and they only live for a couple microseconds and they're gone. And so it makes it very challenging to do any kind of normal calorimetry experiment to figure out the enthalpies. So the way they do it is they have to combine a whole lot of different measurements in clever ways. So for example, for methyl radical, the way that it was determined was they did a kinetics experiment that put one constraint on what the enthalpy must be. And then they did photoionization spectroscopy, which gave another constraint on it. And then they did some electronic structure calculations to calculate some of the vibrational frequencies to get another constraint. And then by combining these all together, UPAC got together a committee and recommended the heat of formation is this, which is pretty darn good, 0.3 kilojoules per mole. It's a very highly accurate number. And also I'll show you what they actually, where the data came from. This first, what they did was they reacted methyl radical with HI and measured the rate coefficient. And then they did the reaction in reverse. They reacted I atoms with methane, and they measured that rate coefficient. And so they measured the forward and the reverse. And from the ratio of the forward to reverse, you get the equilibrium coefficient, the equilibrium constant. And the equilibrium constant is related to delta G. So now they have a value of delta G of the reaction. They did this at several different temperatures. And from the temperature dependence of delta G, you can infer delta H and delta S separately to some extent. So that was one type of experiment they did. And you can see here's a very nice experiments for some of the alkyl radicals reacting with iodides. And they did a lot of different temperatures. And then they did the reverse experiments. There's a lot of kinetics experiments here, all pseudo first order. Then they also did a photoionization experiment. So the way this works is they took the methyl radicals, they made them somehow, which is tough, and then they blasted them with a vacuum ultraviolet photon, and it kicked out an electron, and they detect the appearance of the methyl positive ion and the electron. And they varied the wavelength of this light, and they saw, so here it is. So they made methyl radicals, and as they made the wavelength of the photon shorter, they start to see some ions, and then they see a lot of ions. So somewhere in here is the threshold for when the photon had enough energy to kick out an electron to make the CH3+. Now you might think it was here where you first start to see the deviation from baseline, but one problem you have is that the methyl radicals, some of them might be hot. They might have vibrational energy in them before you start, and so these guys down here are probably the hot ones, and this main band is probably the cold ones, the ones that don't have very much vibrational energy. Those ones are like the Boltzmann maximum. And so you have to do some complicated deconvolution of the temperature to figure out how to interpret the shape to get a sharp number for the ionization energy. So they did that for reaction 1. Then they did the same thing. We started with methane, and they put higher energy photons in, and at high enough energy, the methane fragments, and it makes CH3+ plus an H atom plus an electron. And they measured these guys appearing. And here's the CH3+ appearing from methane, and you see it goes up. You notice the signal to noise is better here because they have a lot of methane, because you can buy methane in a bottle and just put as much methane as you want. Here they had to make the CH3, so they probably had a really tiny concentration of it, so it was a pretty hard experiment to do. Then if you take those two numbers, the onset energies here, and you take the difference between them, and you do a thermochemical cycle, you see it turns out to be CH4 going to CH3 plus H, which is the bond dissociation energy we wanted. And since they know the thermochemistry of CH4 and they know the thermochemistry of H, now you can infer from that difference the enthalpy of CH3. Does that make sense?
Is that really photoionization or multi-photon ionization?
I think this is single photon because they have to know exactly the wavelength to know exactly how many photons. If you do multi-photon, the problem is you don't know how many photons are absorbed.
Right.
Yes, this would be a single photon.
It's hard because I know the energy for reading one of the electrons off is much bigger than what usually lasers have.
Yeah, that's right. So you can't do this with a laser. So nowadays they do this with a synchrotron. I think back when they did this, they had sort of like X-ray machines, but the intensity of the light source was very weak. So they didn't have very many photons. And also it's in vacuum ultraviolet, which means that you can't it'll be absorbed by the air. So you have to do all the experiments in vacuum. And actually most of the window materials will absorb it too. So this is technically not a very easy experiment. They have to use very thin windows. You don't have any lenses. So you have to use fancy grading things to try to direct the beam and stuff. It's just not easy experiments. But it's very definitive. So if you see that threshold and that threshold, you subtract those two numbers, it's hard to understand, it's got to be this energy of this reaction. It's hard to see what else it could be.
And how do you know that the ionization was just because of one photon and not multiple?
I think they would typically vary the flux. But I think in these experiments, when they did it at the time, the number of photons they had was so small, it was like they're getting one at a time. And then they would count. They'd have a counter to count each electron that came and each ion, they'd have like 2 counters, and only keep ones that were coincidences. It's sort of like particle experiments the physics guys do. You know, those kind of detectors. But nowadays with the synchrotron, you have so many photons, you can actually just stick a regular mass back in there and you'll see a signal. But I think back when they did this, it was harder. And then they also calculated the frequencies with quantum mechanics, and here they used the B3 lit method, which was the most popular method around 2000. Maybe even up to 2005, 2010. And with this method, you calculate the frequencies, and some of the frequencies you calculate dead on. So here you calculate this frequency, 3004, it's 3004. But some of them are off. So here's the calculation for the umbrella vibration. You calculate 523, the experiment is 606. And what's happening here is that the real umbrella vibration is not harmonic, it's not parabolic. So if you look at the V as a function of the angle that corresponds to there's sort of an angle, say, out of the plane. So these guys are doing an umbrella vibration, all going up to invert like your umbrella in the wind, flipping through. V is a function of this phi. It's not a perfect parabola like you'd expect. It's more like this. Something like that. It gets steeper as you go up. And so if you do a small amplitude calculation here for this real, let's do the real potential like that. It's pretty flat, so you get a low frequency. But the experiment is measuring the real energy difference between the 0-point energy and energy up here, this difference. And that difference doesn't really exactly correspond to this because it's so much affected by the stiff wall. So anyway, this kind of stuff, it causes massive problems for the poor quantum chemists. And they have whole conferences discussing why is the methyl vibration off, and is it because our calculation method is bad, or is there something about the interpreting experiment we're doing wrong, or what? And then try to figure it out. Because you can see the other ones are all pretty good, right? These other frequencies are calculated pretty well.
I have a question.
Yeah.
What's the scaling?
Okay, so the people who invented this method.
Can you repeat the question?
Sorry, the question is, what is the scaling? It says it's scaled here. So the people who invented this B3 lit method, they immediately calculated a bunch of regular molecules, regular stable molecules that everybody knows the frequencies of for a long time. And they found out that they systematically over-predicted the frequencies by 4%. So they said, multiply all our numbers we calculate with our method by 0.96. That's the recommendation in their paper when they invented this method. Because they knew their method was approximate to start with. And on top of that, all molecular vibrations are anharmonic. They're not exactly harmonic. And typically, actually, they typically have inharmonicities that are sort of a few percent. So it could be that their method is actually perfect, and it's just that the molecules are really not parabolas. And so that could explain it. Maybe. That's what they said. Okay, but if somebody invents a method, an approximation method, and they say, do it this way, do it that way. Okay? The poor graduate student did their whole 5-year PhD trying to figure out the best way to do it. And they published a paper and said, this is the way to do it. Do it. Okay? Right? So everybody does it. So they said multiply by 0.967. Okay, so everybody does it. 0.967. Everybody looks at that, and they, immediately it's warning you, like, this method is not perfect, right? Obviously, they wouldn't have a correction factor in there. But, perfection's hard to achieve. Yeah?
This level of theory is pretty low nowadays. So do you check with some higher level calculation for those frequencies?
So I have not, but I'm sure that actually everybody who invents a new method will do methyl because it's really easy to calculate. So there's probably 1,000 papers that all have every different approximation method using methyl, and I don't know which one's the best. Yeah. And I think this problem with the new 2 mode, this is famous, and it has to do with the potential is not harmonic at all. So the experimental number is affected a lot by the fact that it's not harmonic. All right. All right. Sometimes you can measure the equilibrium constant instead of measuring the rate coefficient forward and reverse and inferring the equilibrium constant. Sometimes you can just measure the equilibrium constant because you can get, say, two radicals in equilibrium with each other, and if you have good absolute calibrations, you can measure the actual ratio of the two radicals. And so that's what was done here, that they did reactions of the H atoms adding on to ethylene, but then this thing called, to make ethyl radical, the ethyl radical falls apart. And so what you see is that the, you can see it too well, this plot here, but this line here does not match up this guy. There's a little offset. And that's because you have some of the H atoms are left. They won't all react because this guy spits out some H atoms. There's an equilibrium level. So the H atoms decline until they reach their equilibrium level. And by very carefully measuring that deviation between this flat asymptote and that value here, then they were able to infer what the equilibrium constant was directly over in some temperature range where they could do the experiments. And then they did different temperatures, and they used other information they had about the thermo, about these guys, and from that, putting that all together, they could get a good estimate of what the delta H was for the C2H5 radical, the ethyl radical, which is a very important one for combustion. And there's several different ways to try to do the extrapolations and how to interpret these experiments. And if you get into it, there's like a second law method and a third law method, and they're good for different purposes, and they should agree. I don't have a picture here, but I think later I'll show you a picture where they don't always agree exactly. And then there's a big discussion in the thermochemistry community about exactly what the numbers should be. And you know, when you end up with these numbers, they always have an error bar, right? So the whole game is trying to figure out what the real number is with the error bar and trying to make the error bar smaller and smaller. And you have to carefully consider all the sources of the error, both the actual measurement error you see, but a lot of it's the systematic errors in the way you do the analysis. So there's people have done this to try to figure it out. So for fuel chemistry, we really care about the thermochemistry of the radicals of the fuel. So that you have a fuel molecule, it's stable. Usually the way the fuel falls apart is that some radical attacks it, pulls off one H atom, and now I have a fuel radical. It's like the fuel molecule minus one H. And that's going to do all kinds of stuff. And a very crucial number when I compute the kinetics is actually the thermochemistry of that radical, because it controls how fast it will be formed by abstraction to begin with, and also a lot of the rates of what happens next depend on the thermochemistry. And so another way to report that thermochemistry is this bond strength. How much energy does it take to rip an H off of my fuel molecule? And that's just the heat of formation of the radical, heat of formation of H, and the starting fuel. So these guys, H is well known. This, your fuel molecule you can measure with bomb calorimetry, and so now you can use this to try to infer this. And these numbers have been tabulated because they're so important, and there's many actually papers. This is actually a relatively old paper, 1994, but there's a more recent people try to keep track of these things. And then you can add in the PV if you want to get the enthalpy and so on. And other people do things called gas phase acidity, where you put the molecule in the gas phase and you expose it to, say, some protons, and some of the protons stick to it. And you can figure sort of how it is as a base in the gas phase. And you can also, then you can do thermochemical cycles with those guys as well. And also you can have things rip an H off of your molecule and make the anion. So you have all kinds of reactions in the gas phase. And so inside a mass spectrometer, you can react it with all the different ions and do thermochemical cycles based on those guys. And they also give you other estimates of the enthalpy. So you get a lot of different ways to try to get estimates of the enthalpy. And the big innovation in the last 10 years was the idea to try to combine systematically all of those different types of measurements together, as well as all the calculations we can do, and try to get the very best numbers for all the thermochemistry. And this is called the active thermochemical tables approach. And it's active means that every time a new piece of data comes in, all the numbers of enthalpies of everything are recomputed to be consistent with all the experimental data that's available. And so it's like an evergreen thing. That every time somebody makes some new measurement or new calculation, everything gets recomputed and you get better error bars. Error bars get tighter and tighter, hopefully. Or else you get some big alarm bell saying this new data is incompatible with all the previous data. And then you have to do experiment, figure out which experiment was wrong. And there's another paper about this, another method called NEAT, which is sort of similar to this one. I think before I talk about that, maybe you guys give me a break. So let's take a break and then we'll